Let's take a look at an application of Avogadro's law. Now, say we have a tank of propane, right? This here is the chemical formula for propane, and it reacts with 5 gaseous oxygen molecules to produce CO2 in water. Typical combustion reaction. Now, we want to figure out how much oxygen it takes to react with 2.7 liters of propane, right? How many liters of oxygen does it take to react with 2.7 liters of propane? Now, this is new for us. We've never seen liters before. We haven't really used that as a measurement of a gas or any kind of molecule before. So let's see what we can do. Well, conceptually, this is all happening at the same temperature and the same pressure, 25 degrees Celsius and 760 torr. So if these are happening at the same temperature and pressure, then however many moles are in 2.7 liters of gas, of propane, should give us an indication or some sort of relationship with however many moles are in the volume of oxygen. So what we can actually do is use Avogadro's law to convert the liters of one gas into liters of another gas. Let me show you what I'm talking about. So we have our propane, and it is 2.5 liters. Now, if we had grams here, we would say that X amount of moles reacts with, or 1 mole reacts with 5 moles of oxygen, right? So if we were dealing in grams and moles, we could say, oh yeah, 1 mole of propane is going to react with 5 moles of oxygen. We can do the same thing, but with liters, so long as the temperature and pressure stay the same. So we can say 1 liter of propane gas is going to react with 5 liters of oxygen gas. All right, and we can say that as long as the temperature and pressure stay the same. So we have 2.7 liters, and we say that 5 liters of O2 reacts with 1 liter of C3H8. Then our liters, or our volume of propane, cancels, and we're left with 13.5 liters of oxygen. So that's pretty cool that we could figure out the volume of a gas we would need just from the chemical reaction. So because these two react in a 1:5 ratio, that's going to stay true for their volume as long as pressure and temperature stay the same. Let's look at another application of this phenomenon. Right? Say we have a mass of gallium. Right? We're going to take 8.88 grams of gallium. Right? And that gallium is going to react with hydrochloric acid to produce hydrogen gas. The reaction for this is 2Ga plus 6HCl yields 2 gallium chloride and 3H2 diatomic hydrogen gas. All right, so that's our chemical reaction. Now this reaction is happening at 27 degrees Celsius, and it's happening at a pressure of 723 torr. All right, now we want to know how many liters of hydrogen is going to be produced from this reaction. So we're starting out with a mass of gallium, and we want to know how many liters of hydrogen is going to be produced. All right, now this might be a little bit more complicated than our last example, but we have everything we need. And what we need to use is the ideal gas law. So PV equals nRT. Make that capital T, right? We're looking for a volume, right? And what Avogadro's law tells us is that if pressure and temperature stay constant, which they are, we can actually use the molar relationships of these gases to make a volume relationship between them. So the first thing we're going to want to do is convert gallium into moles. So 8.88 grams of gallium, right, times 1 mole divided by the molar mass of gallium, which is 69.723 grams. All right, the grams of gallium are going to cancel, and we're going to get 1.131 moles. Now, we're not quite done yet, okay? So we're looking for the liters of hydrogen, which means in our formula, in our ideal gas law, we're going to want to plug in how much hydrogen is being produced. So gallium reacts to hydrogen in a 2-to-3 ratio, right? We have 2 gallium here, 3 hydrogen gas here. So to produce our moles of hydrogen, we need to run it through that ratio. So 0.131 moles times 3 moles of H2 divided by 2 moles gallium. All right, so we multiply this by 3 and divide it by 2, and we're going to get 0.951. Now, I will say, I'm going off my notes here, and if you round this number early, you do get a different number than what they have in the book example. So if you're going straight through your calculator, you'll get a different number than if you round it off to 3 sig figs and then put it in your calculator again. Either way, it won't affect your answer that much, but just be aware of that. If you want to be exactly like the book, then don't round your sig figs until the end of the calculation. All right, but we have our moles of product, and now we just have to plug into the ideal gas law. But remember, this R has a lot of weird units, and these units aren't Celsius and torr, so we need to convert those as well. So we need to convert pressure into atmospheres. So 323 torr times 1 atmosphere, where 1 atmosphere is equal to 760 torr. All right, setting up the conversion factor from torrs to atmospheres, we get 0.951 atmosphere. And I realized that my moles for hydrogen was way off. Sorry about that if you were following along. It's actually going to be 0.191 moles of hydrogen. So a little confusion there. Sorry for that. 0.591 is the atmospheres. 0.191 is the molar mass. Or amount of moles, not molar mass. All right. Next thing we need to do is temperature in degrees Celsius plus 273 to get Kelvin, and that is going to be 300 degrees Kelvin. Now, we're going to plug all of this into our ideal gas law. All right, first, let's clear out some space and write in our new values. So we have 300 degrees Kelvin, 0.951 atmospheres, and 100.191 moles. All right, let's clear out some space, and then we'll use the ideal gas law to solve for our volume. Okay, so PV nRT, we want to isolate volume on its own since that's what we're looking for. And that's going to be the number of moles times our constant times our temperature divided by our pressure. So number of moles first, 0.191 moles times our constant, 0.08206. And then remember the units on this is funky, but it's going to be moles and Kelvin on the bottom, and then atmospheres and liters on top. All right, and then at the end, we're going to put our temperature, 300 degrees Kelvin, and divide all of that by our pressure, 0.951 atmospheres. All right, putting all of that together, we come out with 4.94 liters. And so what that means is if 8.8 grams of gallium were to react with hydrochloric acid, we would get a volume of almost 5 liters in diatomic hydrogen gas. Right? So just to review, we went from grams to moles for this gallium, then converted it into the moles of product using our 3:2 ratio, 3:2 product to reactant ratio. We had to convert our temperature, convert our pressure into atmospheres, and then we used the ideal gas law to solve for volume.